Printing technologies based on drop-on-demand are known for decades. The drop generation basics and its applicability are extensively studied in the past. Recently, more emphasis has been given in building a single platform device that can be used for different applications. This calls for working on the basics of printing, that is satellite-free drop generation, thicker line prints, larger particle print, etc., which are important to acknowledge. Researchers from Center for Nanoscience and Engineering, IISc Bangalore, developed a new printing technique that generates satellite-free drops and is used for printing thicker lines without clogging the nozzle. The uniqueness of this technique is the use of superhydrophobic mesh for printing, replacing conventional nozzle-based systems.
In drop impact printing, we use the kinetic energy of a falling droplet on a superhydrophobic mesh to generate smaller droplets. The size of the ejected droplets can be controlled by changing the pore openings of the superhydrophobic mesh. This unique way of printing is economical and simple. Nozzle clogging is a major problem in most of the existing printing techniques. In drop impact printing, as the superhydrophobic mesh is used, it doesn't allow the falling droplet to stick to the superhydrophobic mesh, and hence in this particular technique we can print particle suspension with very high mass loading. This is the advantage of drop impact printing technique. This technique can be used to print area of live cells, bacteria. This can be also used to print electronic circuits, and this can be also used structuring functional nanomaterials.
The liquid called inks is filled in an ink reservoir and is pumped to syringe through micropipes. The drop generated from syringe from an optimized height was impacted on superhydrophobic mesh to eject a single drop. The drops were collected on substrate kept beneath the mesh. For initial proof of concept, the researchers took water as ink to print through different pore opening meshes, and it was observed that the lowest ejected drop size is 40 microns.
The question is, how does this droplet ejection take place? And more importantly, why does it take place during the recoil phase? Upon further investigation, we found that when the droplet hits the superhydrophobic surface, a cavity is created at its center, and when this cavity collapses, momentum of the interface is higher than the momentum of the actual impacting droplet. This leads to formation of a jet, and which breaks to give us a single droplet.
The research group demonstrated that this technique can potentially and precisely print drops at very high accuracy. This acts as a plus point for applications where accuracy matters a lot.
In bioprinting applications, reagent mismatch is a major problem. With drop impact printing, we can print droplets containing live cells ranging from nano size to micro size with very high precision.
Moreover, for circuit printing and 3D structure printing, this technique performs well. The thicker line printing in one go gives us the required features and properties. This not only saves time but also maintains the integrity of the structure.
Researchers suggest that the proposed printing platform can be used for greater number of advanced applications in coming future, such as in pharmaceutical industries for gel-based capsules, for large area lens manufacturing, and many more.